Good day. For those of you who do not know us, we are the instructional staff for ECE 150. Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we are going to discuss functions on objects. That is, functions that take objects as arguments. So, in this lesson, we will look at functions that investigate and manipulate objects. So we will describe functions that will investigate or query objects. That is, their purpose is to access values stored in member variables and return an appropriate result based on what is stored. We will also describe functions that manipulate or modify objects. That is, they are going to modify the values that are stored in member variables to suit a particular purpose. We are going to look at a number of examples, including a three-dimensional vector class, a rational number class, an array class, and a pair class. So let's consider this 3D vector class. We have three member variables, x, y, and z, and we suffix each member variable with an underscore. Recall that reserved words or reserved identifiers begin with an underscore or contain two underscores. Now, let's start writing some functions associated with your linear algebra class, the inner product or dot product, and the two norm or Euclidean norm. Also, we will take the sum of two vectors and calculate a scalar multiplication. We will also look at calculating the cross product and the projection. First, let's implement the inner product or dot product of two vectors and then the two norm or the Euclidean norm or Euclidean length of the vector. First, the inner product is just the sum of the pairwise products of the entries of the two vectors. So we just calculate this value and we return it. With the two norm, one could perform a similar calculation. However, from your class, you know that the two norm of a vector is the square root of the inner product of the vector and itself. So consequently, why not use the function that we have already written to make that calculation rather than making a similar calculation once again? Here are the vector space operations of vector addition and scalar multiplication. Once again, we don't expect these functions to change anything, and therefore all the parameters are declared const. For vector addition, the sum of two vectors is a new vector where each of the entries of the new vector is the sum of the corresponding entries of the original two vectors. The scalar multiple of a vector by a scalar A is just a new vector where each entry is the original vector multiplied by A. Now, you may want to write down, for some reason, a vector times a scalar, but that's equal to a scalar times a vector. So if you wanted to write it in the other order, well, the easiest way to implement this is just to call the function with the arguments in the opposite order, because we've already implemented that. Now, as far as implementing both the projection and the cross product, both of which return a three-dimensional vector, we should first look at the definition. Recall that the projection of a vector u onto a vector v is just the inner product of v and u over the inner product of v and v, all multiplied by the vector v. Now, you might want to implement this, but notice that each of those operations has already been implemented. we've already written functions that calculate the inner product of two vectors, and the ratio of two inner products is a scalar, and we have therefore already implemented a function that does scalar multiplication. So the projection can be written very simply as the multiplication of the ratio of the inner product of v and u over the inner product of v and v, and this is the first argument of a multiplication with the vector v. So the functions we have already written do all the work to calculate the projection. Unfortunately, there's no such easy way of calculating the cross product, so for that we simply have to hard code it, and for the cross product we have to make absolutely sure that our entries are correct. That is, we are multiplying and either adding or subtracting the correct pairs of entries. Again, this is something you can look up in your textbooks in linear algebra. However, once you've implemented it, that's it. You don't have to implement it again. Finally, we may also want to test if two vectors are equal. And from your linear algebra course, you know that two vectors are equal if all of the corresponding entries are equal. Consequently, all we do is compare the corresponding entries and ensure that all three of them are equal. Next, let's look at some functions that modify a vector. From your linear algebra course, you know that any vector that is not the zero vector can be normalized, that is, made into a unit vector. Additionally, we may want to have something that is similar to plus equals and times equals, but now for vectors. So given a vector, we may want to add onto that vector another vector, or given a vector, we may want to multiply each entry in that vector by a scalar. This differs from the two previous implementations we had, which just took two arguments and returned a new vector. So, to modify a vector, it's necessary to pass it by reference, but not by constant reference, as we wish to change the member variables. Now, for the normalization of a vector, the first thing we have to do is calculate the two norm, because we will divide every single entry of the vector by the two norm, but only if the two norm is not equal to 0. So once again, we calculated the norm of u and we assigned it to a local variable that has an appropriate name. Then, if the norm is not equal to 0, then we divide each entry of the vector by that two norm. Also, if we want to add a vector v onto a given vector u, or multiply a vector u by a given scalar a, again, we can pass the second argument by constant as a constant, but the first cannot be. And again, we do have to pass the first by reference, as we want the original vector to be changed. So here we pass u by reference and v by constant reference, and thus we can add the corresponding entries of v to the appropriate entries of the vector u. The same goes for multiplying each entry of the vector u by a constant scalar a. Next, let's consider a rational number class. All we will be doing in this class is storing the numerator and denominator as integers. So here's our class, and it's reasonably straightforward. And we will call the two member variables numer and denom, as otherwise the identifiers would become too unwieldy. We're going to implement similar operations on rational numbers, but again, now some of the operations will be a little bit more involved than they were for a simple class such as a vector class. Now, from your course in linear algebra, you know that the properties of vectors differ from the properties of fields, and fields are classes such as rational numbers, real numbers, and complex numbers. Now, we can implement functions that now perform operations on rational numbers, such as adding two rational numbers together, or perhaps adding an integer onto a rational number. Now, from elementary school, you know this is the formula for adding two rational numbers. The numerator of the first times the denominator of the second, plus the numerator of the second times the denominator of the first over the product of the two denominators. So this is something that we can implement easy enough in C++. Now, the next step is adding an integer to a rational number. Now, if you work out the math, this is the formula. And so we could instead implement this formula. However, instead, since we've already implemented one function that adds two rational numbers together, and every integer is a rational number equal to that integer over the denominator 1, we could actually just reuse our previous function we just implemented. So therefore, if the first function is correct, so is the second one. Now, some of you may argue this might actually be a poor choice because the formula for adding an integer onto a rational number requires fewer arithmetic operations than adding two rational numbers. True, so in that case you may actually decide to implement the description we see here in the given formula. We can also implement functions that multiply two rational numbers or a rational number and an integer. However, this is even easier than addition, as it is for the product of two rational numbers, it's simply the product of the numerators over the product of the denominators. Easy enough. Now, for calculating the product of a rational number and an integer, you could just calculate the numerator of the first times n all over the denominator of the first, or, as before, we could just create a new rational, and that rational is n over 1, and we can call the previous function that multiplies two rationals, and you should expect the same answer. Once again, it might be more intelligent to simply implement a new function that requires one fewer arithmetic operations. However, what we're trying to emphasize here is always think, where can you reuse a function that you've already implemented and tested rather than writing a brand new function from scratch? Now, we may also want to negate a rational number or calculate the multiplicative inverse. These are reasonably straightforward. We just generate a new rational number and let's negate the numerator for the additive inverse. And for the multiplicative inverse, we simply assert that the numerator is not 0 and then return the rational number where the denominator becomes the numerator and the numerator becomes the denominator. Of course, if the numerator is 0, you cannot calculate the multiplicative inverse. We can also implement a function that calculates the absolute value of a given rational number. Now, for this, we will need the CMath library since we're just going to use the absolute value function, and we will simply return the absolute value of the numerator over the absolute value of the denominator, as after all, either of these may actually be negative. Now, let's write some functions to determine when either two rational numbers are equal or a rational number is equal to a given integer. Now, from elementary school, you know that two rational numbers are equal if, when you cross multiply, the numerator of the first times the denominator of the second equals the numerator of the second times the denominator of the first. This is something that we can, of course, implement in an easy enough manner, and consequently, we can also implement an equals function when comparing an integer simply by calling equals with the rational number n over 1 as a second argument. Now, how about let's do some comparisons of rational numbers. So, if we want to determine if a rational number p is less than a rational number q, then you may think, oh, well, let's use the same formula. The first ratio is less than the second ratio if, after cross multiplication, the first product is less than the second product. And if you thought this, you may implement it as follows. And you'd be correct most of the time, unless one of the denominators is negative. For recall that if we were to calculate 1 over negative 1 being less than 1 over 1, which is true, negative 1 is less than 1, then using this formula we would now determine if 1 is less than negative 1, which is false. Now you have to go back and think about comparisons and multiplying both sides by negative numbers. If you multiply both sides of a comparison by a negative number, then you have to change the sign of the comparison. So if a over b is less than c over d and b is less than 0, this is true if and only if a times d is greater than c times b, assuming, of course, that d is also positive. Thus, the implementation of a comparison operation for rational numbers is slightly more complex. So, if both denominators are positive or both denominators are negative, then we can use the standard formula. However, if this condition is false, then exactly one of the two denominators is negative, in which case we have to change the orientation of the comparison. Now, how about converting a rational number to a double precision floating point number? So basically converting a rational into a real number. Well, we cannot just divide the numerator by the denominator since they are both integers. However, we could tell the compiler, oh, let's multiply the numerator by 1 as a floating point number, in which case it will convert the numerator also into a floating point number before it computes that number times 1.0, which doesn't really change it, and then now we must divide it by an integer, but to divide a float by an integer, the compiler must determine, yes, the denominator must also be converted into a float, in which case the division is performed as a division of two floating point numbers. Instead of tricking the compiler to converting an integer to a double, we can just explicitly tell it to do so. So, static cast with a type between two angled brackets tells the compiler to convert the object that is in the parentheses to the specified type. That's it. So static cast means it happens at compile time and the conversion is performed by the compiler. At least the compiler sets the conversion up. Now, you don't really have to convert the denominator into a double because once again, as soon as the numerator is converted to a double, then for the division to occur, the denominator must also be converted to a double. However, this is a lot clearer for the reader. Yes, you do intend for this division to be a division of two floating point numbers. Alright, so here we've introduced something slightly new, the ability to explicitly tell the compiler to change the type of some particular, well, in this case, a member variable, but you can do it for a local variable or a parameter as well. Now, recall that we previously had to create an array which was stored as either a local variable or a double, but in any case, the array entries were stored in one variable and the capacity needed to have been stored in another variable. So this sounds like the ideal situation for a class. We'd like to store in one class both the address of the first entry of the array and the capacity of that array. So the first thing you may think is maybe we could do something like this. We could somehow have a capacity, which is a member variable of a class, and then we could declare the array to be an array of that many objects. That's a nice idea, but there's one serious drawback in C++. C++ does not allow for any class which it cannot immediately determine the size of the class at compile time. What that means is I can have an array class that has an array of size 50, but I cannot have one where you decide how large the array is. So, how can we solve this problem? Therefore, in C++, arrays of that are member variables of classes must either be fixed in capacity or they must use dynamically allocated arrays. That's what we're going to do here. We're going to declare an array class that stores a capacity and then the address of, in this case, a double. So we could use this array class as follows. First, we declare my array to be an instance of the array class, and we initialize the two member variables in order. First, my capacity is set to 32, and the array member variable is initialized with the address of a new array of 32 doubles. Now, of course, the person using this array class had better make sure that the numbers match. So if you do not match those numbers correctly, then the array class instance, or the object, would be out of sync with itself. Next, let's walk through the array and initialize each entry of the array to 1.5. Well, actually, we're setting each entry of the array to 1.5. We cannot do this during the initialization phase because this would require us to have a fixed number of 1.5s in the initialization list, which is somewhat suboptimal. Alright, then we can use the array, and then we can deallocate the memory for that array, set the array member variable to null pointer since we have just freed that memory. We do not want a dangling pointer, and just to make sure we can set the capacity to 0. So if the capacity is 0, the array cannot store anything, and if the array member variable is null pointer, then yes, this array cannot store anything. So that's an appropriate value. Now, the initialization of the array and setting all of the entries of the array to a specific value is something that we might want to do quite often. So it makes sense to instead have this as a completely separate function. So we may have an array init class or initialization. So we will pass it the array and the capacity we want, and the initial value each of the entries of the array should be set to, and that will have a default value of 0. So here's our function. Once again, we do have to check. Let's say that the member variable array is not equal to null pointer. Well, that means that either the user made a mistake or the array has already been initialized. So, assuming that the user is calling this array init class to initialize or perhaps reinitialize an array, we will delete the array and set that member variable to null pointer. We will also, of course, set the capacity to 0. Now, we will set the capacity to the new capacity that is passed as a parameter, and we will initialize we will set the array member variable to be the address of a new array of the new capacity we just assigned. Then we can create a for loop which walks through the array and sets each entry of that array to the initial value. We could also have a separate function that does the cleanup. So the cleanup function would deallocate the memory for the array. And something that's nice is in C++, if you happen to call delete or delete with square brackets on a null pointer, nothing happens. It's not an error, simply nothing will be done. So in this case, we do not have to check if the array member variable was set to null pointer. After that, we can set the array member variable to null pointer and the capacity to 0, and we are done. What's nice with a function is if at some point you also decide that it is important to set all of the entries of the array to 0 before you deallocate the memory of the array, then you only have to do it once in this function and not every time you clean up an array somewhere within your code. We can now use these initialization and cleanup functions inside our program. So now my array is initialized with everything to the default value. That is 0 for the capacity and null pointer for the array member variable. Then we call array initialization, pass it my array, indicate that we want the array to have a capacity of 32 and that each entry of that array should be initialized to a value of 1.5. At this point, the program can use the local variable myArray, and once we are done with it, we can call on myArray the cleanup function. Nice. That will deallocate the memory, set everything to either null pointer or 0, and we don't have to worry about any dangling pointers. We could have other functions, such as array reset. This takes an array and is going to assign to each of the entries of the array a new value, which has a default value of 0. So, in this function, of course, we do have to be careful, just in case the user passed us an array where the array member variable is null pointer, then there's nothing for us to do. So we're not even going to do anything, we'll just return. However, if the array member variable is not null pointer, we have a for loop that steps through the array and assigns each entry of that array the new value. You'll remember before we implemented a function that calculated the average of the entries of an array. We could do that with this class as well. So here's our array average function. Now, once again, we have to check, just in case the member variable array is null pointer, there's nothing to calculate, so we're just going to return 0 as the average. Otherwise, we will have a local variable sum, which is initialized to 0, and we'll step through the array, adding to sum each of the entries of the member variable array. Having done so, we will then return the sum divided by the array's capacity, which will, by the compiler, be converted into a floating point number. Now, there are many other functions that you could author that could be implemented with this array class. You could have a function that checks if the array stored in this array class is sorted. You could sort an instance of this array class. You could search an instance of this array class using a linear search. You could search it using a binary search. However, making a better array class is something we're going to leave for later. Right now, our biggest problem is that we are always required to check if the array member variable is null pointer, which seems unnecessary. But remember, the user could accidentally call a member function or call a function when the class has not yet been initialized. But that doesn't solve the problem if the user gives us an array with invalid entries. The first thing we have to do is fix this problem. Once we fix this problem, then we can author a better array class. Up to this point, when a function is meant to act on a specific object, that object is passed by reference, usually as the first argument of the function. This is whether or not the object is being manipulated or changed, or if it is simply being investigated or its member variables being queried. Now, information, however, is generally returned through a return value. Now, we already know that functions can return an instance of a type, be it one of the primitive data types we've already seen, int, double, or an instance of a class, that is, an object. However, up until now, if we wanted additional information returned, what was necessary was to pass additional arguments through reference and then assign those values. So suppose we wanted to write a max-min function for the array class we've just discussed. Up until now, if we wanted to return both the maximum and the minimum entries, or more specifically, the indices at which those maximum and minimum occur, we would have to pass two variables by reference as the second and third arguments. The function would then assign to those arguments the appropriate indices at which the maximum and minimum occurred. Instead, consider the following class called a pair. Now, a pair stores two member variables of type size t, and we're just going to label those member variables first and second. Max min is now going to return an instance of the pair class. And as you can guess by the name, the first member variable will be the index where the maximum occurs, and the second member variable will be where the minimum occurs. At least, if you're going to call the function max_min, that had better be what really is returned. Now, notice that the class declaration comes first. So we are saying pair is going to be a class, but that's about it. In the function declaration, we note that max_min returns an instance of the pair class. And in fact, this is all that is actually needed at this point. All that is needed is that the compiler knows that, yes, there is a class called pair, and max_min will be returning one of these. Once we have all the declarations out of the way, we can then proceed with first the class definitions and then the function definitions. So here we see pair as a very simple class that simply has two member variables. We can now use this pair in a function that we define. So here, first we assert that the capacity of the array is greater than 0. And then we assume that the largest and the smallest element is at index 0. Then we go through the array starting at the next entry, index equal to 1, and we check if that entry is greater than what is currently stored at the index imax. If it's greater, then we update the imax local variable. If it is larger than what's currently at the imax, then whatever is there is definitely not a minimum. So we check. If it is not a maximum, then is it a minimum? If it is, then we update the imin local variable. Having looped through the entire array, we now return a pair where the first entry is initialized with the value of the local variable imax, and the second is initialized with the value of the local variable imin. We can now use this. Here we have an array that is initially of capacity 10. We then ask the user to enter 10 different numbers. Or if this was a sensor, we would perhaps poll that sensor for 10 different values. Notice that when we call max_min, it returns an instance of a pair class, and we initialize the local variable result with whatever is returned by the max_min function. Then we can say the maximum is at whichever entry of the array result.first is, and the minimum is whichever entry of the array corresponds to result.second. Following this topic, you now have seen numerous examples of classes, and you have looked at functions that access and manipulate instances of these classes, or objects. For example, in the vector class, we had functions that took two vectors as arguments, and the return value was a new vector that was the sum of the two arguments. At the same time, we saw a function that took a vector and added to its member variables x, y, and z the values of another vector passed as a second argument. Also, we we created a function that normalized a non-zero vector. For rational numbers, we created appropriate functions to calculate the sum or product of two rational numbers, and we also wrote functions to determine whether or not two rational numbers were equal, or if one rational number was less than another rational number. We then saw an array class, and we implemented some of the functions that we previously implemented on local arrays or dynamically allocated arrays, which required us to pass the capacity as a second argument. By creating a class for an array, then all the information about that class is passed in one object, both a pointer to the actual array and the capacity of that array. And we saw that it made sense to create initialization and cleanup functions, as well as functions that manipulated or accessed the entries of that array. Specifically, at the end, we saw how we can now begin to pass more information back by creating aggregate return types, such as the pair class, one that had two member variables. And when we wanted to return the indices of both the maximum and the minimum entries of a given array, then rather than passing local variables by reference, now instead we return a pair of objects that have the appropriate values in the member variables. Here are the references, the colophon, and a disclaimer. Cheers!